Law of definite composition. The law was stated by French chemist Joseph Proust. The law states that any pure compound always contain the same elements in a definite proportion, by weight irrespective of its source or method of a preparation. The law is also called law of definite proportions. In support of the law, it was experimentally proved that a naturally occurring pure sample of copper carbonate contains 51.35% copper by weight, 38.91% carbon by weight, and 9.74% oxygen by weight. Further, a pure sample of copper carbonate was synthesized in laboratory, and it was found that the percentage by weight of copper, carbon, and oxygen were exactly identical to that of sample of naturally occurring sample of copper carbonate. The law was further supported by different samples of pure water. It was observed that irrespective of sources of water, it contained 88.81% oxygen by weight, and 11.19% hydrogen by weight. The different pure samples of sugar obtained 51.4% oxygen, 42.1% carbon, and 6.5% hydrogen by weight. French scientist Berthollet opposed the Proust's law of definite proportion by giving examples of the substances containing different proportions of elements. However, Berthollet's objections were ruled out, as the experimental work of analysis mentioned by Berthollet was found to be based on impure samples or incomplete reactions. Law of multiple proportions. The law was proposed by British scientist John Dalton in 1803. The law states that, if two elements chemically combine with each other, forming two or more compounds with different compositions by weight, then the masses of two interacting elements in the two compounds are in the ratios of small whole numbers. For example, carbon reacts chemically with oxygen, forming two compounds, carbon monoxide and carbon dioxide. Carbon monoxide is poisonous combustible gas, while carbon dioxide is non-poisonous, non-combustible gas. On analysis, it was found that 1 gram of carbon reacts with 1.33 grams of oxygen to form carbon monoxide, and 1 gram of carbon reacts with 2.66 grams of oxygen to yield carbon dioxide. Hence, the ratios of weights of oxygen to that of carbon for two compounds are: for carbon dioxide is equal to 2.66 grams of oxygen upon 1.00 grams of carbon is equal to 2.66. For carbon monoxide is equal to 1.33 grams of oxygen upon 1.00 grams of carbon is equal to 1.33. The two ratio are in the proportion 2.66 upon 1.33 is equal to 2:1. Therefore, the ratio of masses of oxygen that combine with the same mass of carbon is 2:1. That is a simple ratio. Hydrogen interacts with oxygen to form two compounds, water and hydrogen peroxide. On analysis, it is found that water contains 88.89% by weight of oxygen and 11.11% by weight of hydrogen. Therefore, the ratio of percentage by weight of oxygen to that of hydrogen is equal to 88.89% by weight of oxygen upon 11.11% by weight of hydrogen is equal to 8 is to 1. Similarly, hydrogen peroxide contains 94.12% by weight of oxygen and 5.88% by weight of hydrogen. Hence, the ratio of percentages by weights is equal to 94.12% by weight of oxygen upon 5.88% by weight of hydrogen is equal to 16. Is equal to 16:1. Finally, the two ratios of the two compounds are in the proportion 16:1 upon 8:1 is equal to 2:1. Therefore, the ratio of weights of oxygen that combine with same weight of hydrogen is equal to 2:1. Gay-Lussac's law of combining volumes of gases. French chemist Joseph Louis Gay-Lussac studied number of gaseous reactions and discovered that there is a definite relationship between volumes of gaseous reactants and that of gaseous products. He generalized his observations and stated Gay-Lussac's law of combining volume as: when gases react together to produce gaseous products, the volumes of reactants and products bear a simple whole number ratio with each other, provided volumes are measured at same temperature and pressure. Illustrations. 1. Under identical conditions of temperature and pressure equal volumes, say 1 liter. That is 1 liter of each hydrogen and chlorine gases react together to produce double the volume, 2 liters of hydrogen chloride gas. That is, hydrogen plus chlorine gives 2 hydrogen chloride. 1 liter plus 1 liter gives 2 liters. 1 volume plus 1 volume gives 2 volume. Thus, the ratio of volumes is 1:1:2. 2. Under identical conditions of temperature and pressure, 2 liters of hydrogen gas react with 1 liter of oxygen gas to produce 2 liters of steam water vapor, that is, hydrogen plus oxygen gives 2 steam water vapor. 2 liters plus 1 liter gives 2. 2 liters. 2 volume plus 1 volume gives 2. 2 volume. The ratio of volumes is 2:1:2. 3. Under identical conditions of temperature and pressure, 1 liter of nitrogen gas reacts with 3 liters of hydrogen to produce 2 liters of ammonia gas, that is, nitrogen plus hydrogen gives 2 ammonia. 1 liter plus 3 liters gives 2 liters. 1 volume plus 3 volume, 2 volume. Here, the ratio of volumes is 1:3:2. All examples cited above indicate that, during gaseous reactions, gaseous reactants and products bear a simple ratio of whole numbers of volumes with each other. Volumes may be measured in any convenient unit like liter, milliliters, centimeter cube, decimeter cube, etc. For example, consider the reaction. Sulfur dioxide plus oxygen gives 2. Sulfur trioxide. 200 milliliters plus 100 milliliters gives 2. 200 milliliters. 1 volume plus 1/2 volume gives 2, 1 volume. So that, the ratio of volumes is 2:1:2. Note that, the volumes are not additive. Though, in case of reaction between hydrogen and chlorine gases, it appears that volumes are additive. However, in case of hydrogen-oxygen reaction, 2 volumes of hydrogen and 1 volume of oxygen, equal to 3 volumes of reactants, get converted into 2 volumes of product steam. Similarly, in case of formation of ammonia, 1 volume of nitrogen reacts with 3 volumes of hydrogen, equal to 4 volumes of reactants, get converted into 2 volumes of product ammonia. Avogadro's law. Gay-Lussac's law of combining volumes of gases was stated in 1808. Simultaneously, in the same year, Dalton proposed atomic theory. Avogadro, in year 1811, combined Gay-Lussac's law and Dalton's theory to propose Avogadro's law. It states that equal volumes of all gases, under identical conditions of temperature and pressure, contain equal number of molecules. Avogadro introduced the idea of molecule as the smallest particle of a compound. Dalton believed that compounds are formed when atoms of different elements combine in a fixed ratio. It was firmly believed that the atoms of the same element do not combine to form a molecule. Avogadro suggested that most of the gases do not exist in the atomic state, but exist as polyatomic molecules. Like diatomic hydrogen, H2, diatomic oxygen O2, nitrogen N2 or chlorine Cl2, etc. These diatomic molecules take part in the reaction, as atoms do not exist in free state. That was the most revolutionary idea. Avogadro's hypothesis was published in French journal, Journal de Physique in 1811. The idea suggested by Avogadro was totally neglected by scientist community for over 50 years. The idea of existence of a pure element, as diatomic molecule, was difficult to digest. Finally, in 1860, in the first International Conference on Chemistry, held in Germany, Stanislaw Cannizzaro explained the importance of Avogadro's hypothesis. And only then the precious work was recognized. Mathematically, Avogadro's law is stated as, at constant pressure and temperature, volume of a gas is directly proportional to the number of molecules. V is directly proportional to the number of molecules, where pressure and temperature constant. But number of molecules is directly proportional to the n, the number of moles of gas. Hence, V is directly proportional to n, or V upon n equals constant, where number of moles, n, equals mass of gas, upon molar mass of gas. At STP, it may be possible to calculate volume per mole, V upon n, of an ideal gas. According to general gas equation, PV equals nRT. Hence, at STP, V upon n equals RT upon P, where R equals 0.08205 liter atmosphere, per moles, per Kelvin. V upon n equals 0.08205 a liter atmosphere per moles per Kelvin into 273.15 Kelvin upon 1 atmosphere equals 22.4141 liter per moles. Hence, the volume of 1 mole of any pure gas at standard temperature and pressure is always constant, equal to 22.414 liters or 0.022414 cubic meters. This value is called as Avogadro's molar volume, or molar gas volume at STP. Dalton's atomic theory. Greek philosopher Democritus, in the year 460 to 370 BC, suggested that matter is composed of extremely small, atomio, mean indivisible particles. The tiny, small, indivisible particles of matter were called atoms. In the year 1808, when different laws of chemical combinations were stated, John Dalton, English school teacher, proposed atomic theory. In his theory, made following assumptions. 1. All matters are made up of tiny, indestructible, indivisible unit particles, called atoms. Atoms are the smallest particles of the element, and molecules are the smallest particles of a compound. 2. All atoms of the same element have same size, shape, and mass, and all other properties. Atoms of different elements have different properties. 3. Compounds are formed when atoms of different elements combine. The atoms in a compound unite in small whole number ratios, like 1:1, 1:2, 1:3, 2:1, 2:3, etc. 4. A chemical reaction involves only the separation, combination, or rearrangement, of integer number, of atoms. During chemical reaction, atoms are neither created, nor destroyed. With these assumptions, Dalton explained, law of conservation, of mass. He stated that, during chemical reaction atoms can rearrange and change their partners. Molecules could be decomposed into atoms. But, the total number of atoms in the reactants and products must be same. Hence, mass is conserved during a reaction. Law of multiple proportions was explained by Dalton by assuming that, under some conditions, atoms of two types combine in the ratio 1:1 to form a molecule. Under some different conditions, it may combine in the ratio 1:2, or 1:3, or 2:3, etc. Dalton also proposed some symbols for some common atoms and molecules, shown in the above figure. Oxygen, sulfur, nitrogen, hydrogen, carbon, potassium, water, methane, carbon monoxide, hydrogen peroxide, carbon dioxide.
Subscribe to my channel. Click on bell icon to get notification about new video.